So we've seen the derivation of these equations of looking at the final velocity of the incident or the projectile particle after a one-dimensional perfectly elastic collision, and we've seen the derivation of the final velocity of the the target particle in a one-dimensional perfectly elastic collision. Again, the first particle, the incident particle, is moving, it has initial velocity. The second particle is initially at rest, and after they collide, the first particle has one velocity. The particle that was initially at rest, the target particle, has a different velocity. We'll look at a couple situations here. The first is if the two objects have the same mass or have very similar masses. In this situation, we can look at what each velocity ought to be. We see here, if m1 and m2 are about the same, then this term here is approximately 0. And if this term is 0, that means this whole side of the equation will be 0. And the final velocity of the first particle, the final velocity of the incident particle, will be 0, meaning that the particle is not moving. If we look at the velocity of the target particle, we're saying that m1 and m2 are about the same amount. That's like saying we have 2 times m on top, and we have m plus m on the bottom, because m1 and m2 are both some mass, they're both the same amount of mass. We see here, if we look at m plus m, that's basically 2m, and when those cancel, that's telling us that the final velocity of the second particle is equal to the initial velocity of the first particle. In that situation, you have the first particle is incident on the second particle. After the collision, the first particle is at rest. The second particle is moving in the same direction with the same velocity as it had before. You've seen this happen if you play pool and you shoot a pool ball, the cue ball, at another ball, and they hit head-on. Sometimes the cue ball will just stop and the other ball will keep moving. Sometimes it doesn't, and in that situation there's some more complicated physics going on when you have a spin to the ball that gives it a different reaction. We're not dealing with that right now, though. This is the general case where the first ball should stop and give all of its momentum to the second ball. Another situation is when the mass of the incident ball is much, much greater than the mass of the target. In that situation, when you look at the mass of the incident particle being much, much greater than the mass of the target particle, we can approximate here that this difference is very small. And so this term is basically 0 compared to the very large particle. In the same way, this term is essentially 0 when compared to the very large term. And so if this difference is negligible, we basically have m1 over m1, which is just a 1. That means that the final velocity is 1 times the initial velocity, meaning that this big heavy object is basically moving the exact same at the end of the collision as it was at the beginning of the collision. On the other hand, when we look at the smaller particle, if we're still neglecting the size of the smaller object, then we throw this term out and we have 2m1 over m1. Those will cancel as well, and the velocity of the second particle will be twice the initial velocity of the first particle. And so what we see here drawn out for us is you have a very large particle that hits a very small particle. The very large particle continues onward at basically the same velocity that it had before. The much, much smaller particle is moving twice as fast in the same direction. Now, the larger particle technically has to slow down a little bit. It has to give up a little bit of its momentum in order to accelerate, to give that momentum to the second particle. But we're assuming here that the mass of this object is so small that it's only a very tiny bit of the momentum to get the small object going very, very fast. The final situation that we're talking about is if the projectile object is much, much smaller than the target. In that case, we assume that the projectile, its mass is essentially zero when compared to the mass of the target object. When we throw those terms out, we see we have a negative m2 over an m2. That will simplify to be a negative 1. That means that after the collision, our projectile particle is moving negative 1 times, or has a velocity that is negative 1 times its initial velocity. That means that it has the same magnitude, it has the same speed, but this negative 1 means it is reverse direction. It's bounced backwards off of the big object. Looking at the other object, the target object, its velocity depended on m1, which we're approximating as 0 here. This means that its velocity after the collision is 0 times the initial velocity. And so its velocity is essentially 0. In this situation, the small object is incident upon the much, much larger object. After the collision, the large object basically doesn't move, and the smaller object bounces off in the opposite direction. This is a situation where, for example, you're dropping a tennis ball against the ground. The tennis ball is colliding with the earth, but the earth is so much bigger that the earth basically doesn't move, and the tennis ball bounces off from going straight down to going straight up. So these are all the limiting cases of M1 and M2, and seeing how we can look at the limiting cases, and then any other relation would be somewhere in between for a perfectly elastic collision in one dimension.